theory of celestial navigation, you must go back to ancient days. At that time, men thought the earth was the center of the universe. To them, the celestial bodies, the sun, the moon, the planets, and the stars, all appeared to be moving overhead on the inside surface of a giant sphere. This imaginary sphere has an infinite radius and is concentric with the earth. They gave this sphere a name, celestial sphere, and we still call it that today. From Earth, it appears to move from east to west, one complete rotation every 24 hours. Over the years, astronomers have selected 57 easily identifiable stars on the celestial sphere for navigational purposes. The rest can be disregarded. In addition, navigators have traditionally used the planets Venus, Mars, Jupiter, and Saturn, the Earth's moon, and the sun. To understand how these celestial bodies are used for navigation, you must first review some basic terminology. Let's begin on the Earth, or the terrestrial sphere, as it is sometimes called. The Earth rotates around an imaginary line called the axis. The intersection of the axis and the surface of the sphere are designated the North and South Poles. A plane that cuts through the center of the Earth creates an arc on the Earth's surface known as a great circle. There can be any number of great circles. A plane that includes the Earth's axis creates a great circle known as a meridian. There are an infinite number of meridians, and they all pass through the North and South Poles. The meridian that passes through the Royal Observatory at Greenwich, England, has been selected as the prime meridian. It is the meridian used as the origin for measurement of longitude. Longitude is the angular distance measured at the poles from the prime meridian to another meridian, east or west, from 0 degrees to 180 degrees. The equator is the great circle perpendicular to the Earth's axis. It is represented by the letter Q. Latitude is the angular distance from the equator measured along a meridian north or south from 0 degrees to 90 degrees. The great circle distance of the arc along the Earth's surface is called arc distance. It can also be translated into linear distance. 1 minute of arc equals 1 nautical mile, or 1 degree equals 60 miles. Thus, the 90 degrees from the equator to the North Pole is actually 5,400 nautical miles. A point at 45 degrees latitude is 2,700 nautical miles from the equator. Parallels of latitude are lines on the Earth's surface whose planes are parallel to the equator. The parallels are combined with meridians to provide the grid system that helps you position yourself on the surface of the Earth. There is a similar grid system on the celestial sphere. To begin with, there is an axis, simply an extension of the Earth's axis. The points of intersection of the extended axis and the celestial sphere are called the celestial north and south poles. Polaris, or the North Star, is approximately at the celestial North Pole, and the rest of the sphere appears to revolve around it. A plane through the center of the celestial sphere produces a great circle on the surface. Great circles containing the axis are called celestial meridians when they are projections of terrestrial meridians on the celestial sphere. They are extensions of the meridians on Earth. For example, the terrestrial Greenwich meridian, or prime meridian, extends out to the celestial sphere to become what is called the celestial meridian of Greenwich, or the prime celestial meridian. The great circle perpendicular to the axis is called the celestial equator, or sometimes the equinoctial. It is an extension of the Earth's equator. Celestial latitude is called declination. It is the angular measure from the celestial equator, north or south, to a given point on the celestial sphere from 0 to 90 degrees. There are parallels of declination on the celestial sphere similar to parallels of latitude on Earth. When combined with celestial meridians, they form a celestial grid comparable to our terrestrial grid system. Now we must relate the two. First, assume you are at a specific point on the Earth. The point directly overhead on the celestial sphere is called your zenith. Your latitude and longitude coordinates on Earth are similar to the coordinates of your zenith on the celestial sphere. Conversely, every celestial body has a point on the Earth directly below it. This is called the geographic position, or GP, of the celestial body. Sometimes it is called the subpoint. If you were at the geographic position of Polaris, the star would be directly overhead at your zenith, and you would be near the North Pole. Similarly, if you were at the equator and the sun was directly overhead at your zenith, you would be at the sun's GP. This principle applies to any celestial body, the moon, a planet, a star, or the sun. You are at that body's GP when it is directly overhead at your zenith. Now at this point, we must introduce the concept of apparent motion between the terrestrial and celestial spheres. Using ancient man's concept that the Earth is stationary, we imagine the celestial bodies on the celestial sphere to rotate from east to west. The rate of motion is 1 degree of arc every 4 minutes, or 15 degrees every hour, or 360 degrees every 24 hours. This rotation introduces another term, hour circle, to help locate these bodies at a given time. It is a great circle on the celestial sphere containing the axis and a given celestial body. Let's assume that at a given moment, the sun's hour circle is coincidental with the prime celestial meridian. 4 minutes later, it will be 1 degree to the west of the prime celestial meridian. An hour later, it will be 15 degrees to the west, and so on. We have used the sun as an example, but the apparent motion is common to all celestial bodies. Their hour circles are constantly rotating from east to west. The term that describes the amount of rotation is called hour angle. Hour angle is always measured westerly from a reference point through 360 degrees. In celestial navigation, we use 3 specific hour angles: Greenwich, local, and sidereal, depending on the origin of the measurement. The first of these, Greenwich hour angle, is comparable to longitude on Earth, except GHA is only measured in a westerly direction through 360 degrees, while longitude is always measured east or west 180 degrees from the Greenwich meridian. Using the sun as an example, we may measure its Greenwich hour angle at any given moment from the prime celestial meridian westerly to the hour circle of the sun. This angle is referred to as GHA sun. The Air Almanac lists the GHA of the sun, moon, and planets for any date and time this data is desired. The second of the 3 hour angles, local hour angle, is measured from the observer's celestial meridian westerly to the hour circle of the celestial body. If the observer is at 90 degrees west, and the GHA of the sun is 120 degrees, then LHA sun is 30 degrees. The LHA of other bodies observed for celestial navigation may be computed: the moon, Venus, Jupiter, Mars, Saturn. But when stars are used for navigational purposes, another reference must be used to determine their position. It is the prime hour circle, the hour circle of the sun at the intersection of its elliptical path and the celestial equator as the sun transits from south to north declination. This is the vernal equinox, the first day of spring. The prime hour circle is called by several other names, but they all mean the same thing: the hour circle through the point where the sun's declination is 0. The angular measure from the prime celestial meridian to the hour circle of Aries, the prime hour circle, is called the GHA of Aries. It is listed in the Air Almanac for every date and time, But what the navigator needs to know, of course, is the GHA of the star he is observing. The GHAs of the 57 navigational stars could be tabulated, just as has been done with the sun, the moon, and the planets, but it would require a monstrous publication. Instead, the navigator uses the GHA of Aries plus the third of the 3 hour angles, sidereal hour angle. SHA is the angular measure from the prime hour circle to that of a given star. This angle never changes. This is important. Remember, stars appear to move because of the Earth's rotation. However, they do not change their position relative to one another. So even though the celestial sphere appears to be moving, the prime hour circle and the hour circles of the stars maintain constant relative positions. So the sidereal hour angles, as well as the declinations of the various stars, are considered fixed. SHA and declination for the 57 navigational stars are listed on the inside front cover of the Air Almanac. The navigator can determine the GHA for any navigational star merely by adding its fixed SHA to the GHA of Aries for the time desired. Now let's sum up. When you determine a celestial body's GHA and declination, you know its geographic position or subpoint on Earth. Then, when you actually take a measurement that indicates your range from the celestial body's geographic position or subpoint, you can determine a line of position on the Earth's surface. To determine this line of position, we will utilize the horizon system, which will be demonstrated in Part 2 of this series.